Hello, everyone, and welcome to today's graph reading group.
And today we have Sheng talking about examining graph neural networks for crystal structures. And let's go with that.
So a very quick self-introduction. And as for my academic background, I'm from the discipline of material science. And I got my PhD at the Department of Material Science and Engineering at MIT. And also I got my bachelor degree at the Department of Material Science and Engineering at Peking University in China. And also I have some working experience focused on the materials modeling side. And I used to work as a computational material science intern at Bosch, which is a German materials maker. And now I'm working as a research scientist, computational chemistry at ByteDance Inc., which is the parent of TikTok. So probably now you know TikTok is also working on some materials and chemistry stuff now. And welcome to join our company. Okay. And at the beginning, I want to say something. So this work and I are not from the discipline of computer science. So some of the analysis and the results are not presented in the formal computer science style, like papers in these major conferences. So the purposes of this presentation is to first raise questions to the computer science community. And also I want to chat with the CS community for different opinions and views regarding some stuff in this work. So also a prerequisite is that I know many of you may be familiar with a molecule, but maybe less familiar with crystal. So let me first have a very quick introduction to these two terms. So for molecules, actually we are talking about a collection of finite number of atoms in the three-dimensional space. Just like the figure here, we can see there are some atoms positioned in the space, and we are interested in how this pattern of finite atoms affect the property of the molecule. And when we're talking about crystal, actually we are talking about an infinite number of atoms with periodic boundary conditions. So just like the figure below, when we talk about a crystal, we are talking about many atoms in the space, actually infinite number of atoms. But this infinite number of atoms have some pattern, and we can see that these atoms are crystal are formed with repeating patterns. So when we study crystal and when we talk about crystal, actually what we care about or what we are interested in is the smallest repeating group, like the one in the center. And we call this smallest repeating group the unit cell or the primitive cell of the crystal structure. So with this in mind, we before going forward, actually I want to introduce a requirement when we design neural networks for these crystal structures, which is the supercell size invariance. So imagine that there are some materials properties like the rate of thermal conductance or the hardness. This kind of property do not change when we change the input of the crystal structure. So you can imagine that if we input the smallest repeating group into the neural network, we will have a property predicted by the neural network like thermal conductivity, which is the rate of thermal conductance through the materials. But if we use different inputs, like if we use two of the smallest repeating group to input to the neural network, we should get the same value of thermal conductivity. So when we designing neural networks for crystal structures, for some intensive properties, we have to satisfy the supercell size invariance. Okay, with this in mind, let's go to our work.
Sorry, I have a question regarding that.
Yeah.
For example, if you consider a very simple crystal where you have just carbon atoms, for example, or just lithium atoms, Here, if we take this periodic boundary condition, the supercell size invariance, it would mean that the property of the silicium crystal is the same as the property of the silicium atom. But
yes and no. So I would say, like, if we imagine in the simplest crystal structure, each unit cell only have one atom, for example, one lithium atom. But what we input to the neural network is this one atom plus the periodic boundary condition. So the latest vectors are also input to the neural networks, not just the lithium atom.
Okay, I see. Thanks.
Yeah.
And so another question is, like, for many crystal, the properties are really influenced by some things, like, for example, defects in the crystal that appear very, very rarely. For example, if you're looking at the color of diamond, you'll find very, very rare imperfections in the crystal. Is this something that, like, how do you incorporate that into, like, this kind of condition?
Yeah, that's a good question. So this work do not involve the defect, I would say, in advance. And in real materials modeling, what we typically do is, for example, in this figure, we have 9 unit cell. And when we want to study the effect of defect, we typically, for example, for vacancy, we remove one atom in one unit cell and use the 3 by 3 unit cell to represent the remaining part of the undefect crystal. Okay,
but then you don't have supercell size invariance if you do that.
So you can imagine that, for example, for thermal conductivity, for this kind of intensive property where we should have the supercell size invariance, so the thermal conductivity for the perfect crystal, if we use the 3 times 3, then this value should be the same if we input just one unit cell, right? But when we consider one defect at the central unit cell, for example, then when we input the 3 by 3 supercell, we will have some very little change to the property predicted to the property, because now you can imagine that using the supercell and we remove one atom at the center, this change to the chemical environment will be much, well, the impact will be much less than when we use just one unit cell and remove one atom in the unit cell. I don't know whether my explanation is clear, but
yeah. I think I follow a little, but it's fine. I think you can continue with the presentation. And just to mention, there was a question in the chat here about what do we mean by periodic? Is it related to the periodic table or to the periodicity in translation? And just want to emphasize that here we're looking at periodicity in the translation of the crystal, meaning that the same pattern gets repeated all the time.
Yeah.
So if you can continue to the next slide. Sorry for the interruption.
Yeah. So yeah. Your question about defect is very good, and we can talk about more later if you are still interested in. Okay. So so for the discipline of using machine learning to study materials, just like the molecule, we are interested in using machine learning to predict materials properties like energy, hardness, and thermal conductivity, etc. And when we're doing this, we have to rely on some basic machine learning algorithms like linear regression or random forest or fully connected neural networks to output these properties. But the problem is the same with the molecule, which is that crystal structure cannot be read directly, this basic machine learning algorithms cannot read the crystal structures directly. So we have to also have the step of featureization or to form these representation vectors or feature vectors of crystal structure, and then input these representation vectors to these most basic machine learning algorithms to get the output of property. And in this step, there is a key question is about, do the representation vectors contain all information of these structures? So this work is proposed to actually answer some part of this question. Okay, I think there's a I think there is a question in the chat box. Do I need to answer these questions once they are appeared, or can I just answer them at the end of the talk?
It's up to you whether you think the question should be answered now or not. In that case, we can keep for the end of the talk. Yeah.
Okay. So let me. Okay, I will answer these questions at the end. Okay, so let's continue. And before going to this question, let's briefly review what's the current representation methods for crystal structures. And the first type of representation is human-designed descriptors, which are human non-knowledge of crystal structure. Like for composition part, we can use some simple knowledge of mean atomic radius or standard deviation of electronegativity of composition. And for structure, we can use some simple descriptors like mean bond length and density to form these representation vectors of the crystal structure. And such representation is human understandable because they are from human knowledge, but they only contain information that are currently known to human beings. And I would comment that before the era of deep learning, this kind of human design descriptors is actually the mainstream method to encode the crystal structures. And the second representation is the deep representation learning, which I think is the method that most machine learning people care about. So this kind of deep learning automatically extracts materials representation from structures. And these deep learning methods are thought to be more powerful than human designed descriptors. But we still have a question of how powerful are those deep learning methods? And typically, these deep learning methods are less understandable to human compared with the human designed descriptors. And in the figure below, I just plot a schematic of a very classic type of deep learning method for crystal structure, which is the crystal graph convolutional neural network by Dr. Tianxie and Professor Grossman at 2018. And in this framework, the atoms are seen as the nodes of the graphs, and the bound between atoms are seen as the edges of the graphs. So we can form a multi-graph of the to represent the crystal structure, and using the graph convolutional neural network to connect the multi-graphs with the final output we care about. And actually, in the CGCN I just introduced is a very simple graph neural network structure. Well, you can see that the representation of each node or the representation of each atom is just depends on updated by itself and the messages collected from neighbors. So this is similar to the typical message passing neural network style. And the message, and in CGCN, the messages just depend on the atom type of the center atom and the neighboring atom and the bond length between the atoms. And after all these convolution layers, for the final output, CGCN used the average pooling to collect information from all the atom representations and fit this averaged representation to a fully connected neural networks for the output. And remember, for some properties, we have to satisfy the supercell size invariance, or for many properties, these properties should not scale with the number of atoms. So here we use the CGCN used the average pooling as the default pooling function. And here in this work, we also examine another neural network for crystal structure, which is the atomistic line graph neural network. And in the figure below, this figure just illustrates the main idea of this aligned neural network, which is that this kind of neural network updates the outer representations, bound representations, and bound angle representations by outer type, bound length, and bound angle. So you can see that this aligned framework decode more geometric detail of crystal structures compared with CGCN. And I would say that this field of graph neural network for crystal structures or for geometric deep learning in general is a very hot area today. And I think there are maybe tens of new GNNs proposed per year for these atomic systems. And there are some focuses recently to improve these GNNs, like the equivariance to rotation and the many-body effect. For example, in this aligned framework, it considers the three-body effects, which is the bound angle explicitly. And recently, there are more studies to include even higher order of many-body effect. And also, long-range interaction is another focuses for recent advancement of GNNs for atomic systems, and so on. So, despite this advancement of graph neural networks for atomic systems, or here we care about crystal structure, we still have a remaining question of, can GNN capture all knowledge of crystal structure? And actually, I think we human cannot answer this question because our human beings now only know a limited amount of knowledge about crystal structure. So if we change this question to, can GNN capture all human knowledge of crystal structure, then maybe we can have a way to answer this question. So in this work, we propose that we can use human-designed descriptors as a bank of human knowledge and employ the GNN to learn and predict these human-designed descriptors and use the prediction performance as the metric to evaluate. So you can imagine that if the GNN can predict some of the descriptors well, then we can believe that GNN can capture the knowledge behind these descriptors. Otherwise, if we found that the GNN cannot learn and predict some of the descriptors well, then we can believe that the GNNs cannot capture the knowledge behind these descriptors, so we can partially answer this question. And we think this is a more straightforward way than predicting properties, because if we found that we cannot predict descriptors well, then we directly know what geometric information that this GNN cannot capture. But if we found that we cannot predict some properties well, which is a common thing in recent studies, we still don't know why. And
I have a question, if you don't mind.
Yeah.
If you go back to the previous slides, Yeah. So here there are many things that are inputted. So I just want to be clear that the drawing here is the input to the neural network, or like these are the node feature and edge features that you input at the beginning, right?
Yes. So this aligned framework update these node features, edge features, and this bound angle features, and they have a scheme to initialize this, and during convolution, these features are updated. Yeah.
Okay, I understand now. So you start with a bond length and a bond angle that is approximative, and the neural network has to improve on that and find the right descriptor.
You mean in this figure?
Well, not in this figure, but in general, what you're trying to do with this prediction of the description. So you start with a bond length that is approximative, and you need to predict the real bond length. Is that what's happening, or?
You can So this bound length, I think okay, so the bound length, you can imagine that the bound length in your crystal structure can vary, right? So the bound length between different atoms may be different, but this bound length might be something like the mean bound length of the crystal structure or the standard deviation of bound length distribution, something like this. So yeah, we input the structure and check if GNN can return the correct standard deviation of bound length distribution, for example. Yeah, this bound length is a scalar is a like a mean field or the distribution to describe the whole structure.
Okay, it was just a bit confusing because at the previous slide you said that bound length was an input of note of the edge features, and now it's something that you have to predict. But I understand now what you mean. Thanks.
Yeah. Sorry for the confusion. Yeah.
There's also another question from Sion.
Yes. So could the neural network predict the point group of the unit cells?
That's a good question, and the answer is no. And I will talk about why later. Yeah.
Okay, I have a follow-up question.
Yeah.
So if it cannot predict the point group, then can we just tell the neural network what the point groups are, and then it would be able to, like, because in your paper, I think figure 2, you don't get like 100% bond length and whatever prediction, right? But if we tell the point group, wouldn't that number go higher, and then it could predict the properties better?
Yeah, that's a good question. So later we will show that if we found something that cannot be captured by GNN, like point group or the crystal space group, then we can just incorporate those information in addition to the representation learned by GNN to make a better prediction. Yeah.
Okay, thank you.
Yeah, okay, thanks for the great questions. And yeah, and the next question I want to talk about is if it's similar to what just questioned. If we found that GNN cannot capture all information of the crystal structure, how to incorporate those information? And we can think about this question like we can improve the GNN architecture to incorporate more information. But here we just use a very simple and straightforward way, which is to hybridize descriptors and the graph neural network to make a better prediction. Okay, so the first kind of descriptors we want to examine is some local structure descriptors, and which are essentially statistics of local environments like the mean bound length and the standard deviation of bound angle distribution in this crystal structure. And we can see that both CGCN and align we just introduced before have high prediction R-squared score. And both CGCN and align, which take geometry into account, have better prediction than the composition-only model, which we use as a baseline to examine the ability to capture this property. And yeah, we found that the input of geometric information have something to improve the prediction. And also align is better than CGCN to capture these statistics of local environments, which is reasonable because align take more geometric details into account. And when it comes to some global structure descriptors, we found something surprising. And first of all, we found that both CGCN and align have high prediction R-squared score for some global properties like density, like volume per atom, and like the number of atoms in the unit cell. But we found that both cannot predict lattice constants well, which are the ABC and alpha, beta, gamma on the right of the figure. And this lattice constant actually describes the periodicity of crystal structure. And let me explain in more detail. So ABC represent the length of the lattice vectors, and alpha, beta, gamma represent the angles between the three lattice vectors. And this set of lattice constant is frequently used in the discipline of material science. So we found this phenomenon that GNN cannot capture the periodicity of crystal structures well. And in the following of this talk, we will focus on some brief analysis about why GNN cannot capture periodicity and what's the impact on the prediction of materials properties. So let's have a closer look at the definition of periodicity. So here we want to see periodicity as a structure constraint. So here, if we use the A function to represent the Alton type at position R, then the periodicity requires that the Alton type at position lowercase r plus uppercase r, if this uppercase r is a linear combination of lattice vectors, then the Alton type at these two locations should be the same. And if we simplify the question of periodicity into one dimension, then we can write out the structure constraint that the Alton type at position R should be the same as the location of R plus A, where A is the length of the periodicity. So, and as we introduced before, CGCN and align and most graph neural networks designed for crystal structures, making the prediction by capturing the average local atomic environments due to the design of average pooling. Therefore, given these two definitions, we can see that for short periodicity, for example, the periodicity illustrated by the short red arrow, where we only require that Alton 1 and Alton 3 have the same type and the same coordinate in the y and z direction. Then we can see that the structure within the receptive fields is constrained by this short periodicity. Just like the figure illustrated here, if the receptive field of Alton is from Alton 1 to Alton n, and if the periodicity constrained that Alton 1 and Alton 3 and Alton 5 and Alton 7, something like this, have the same type and the same YZ coordinate, then this structure within this receptive field is constrained, and the GNN may and such constraint might be learnable to the GNN. And how well this short periodicity can be captured by GNN is depend on the local expressive power of the graph neural network. But for some long periodicity, for example, the periodicity that only require Alton 1 to Alton n plus 1 have the same Alton type and the YZ coordinate, then we can see that the structure within the receptive fields is not constrained by periodicity by definition. Therefore, such long periodicity is not learnable to the graph neural networks. And all the analysis above is based on the assumption that the graph neural network is equipped with average pooling. And actually, there is another type of pooling, which is sum pooling. And we can imagine that sum pooling might be better than average pooling for capturing periodicity. But sum pooling is not a perfect solution for this problem because of some reasons, like the presence of intensive properties where we cannot use sum pooling. And actually, periodicity is not extensive. And we will come back to this point later in this presentation. So in this slide, in addition to have a more clear picture of how this length of the periodicity affects the power of graph neural network to capture periodicity, we build a toy dataset of one-dimensional single carbon chains and use the GNNs to predict the periodicity of such one-dimensional structures, where the periodicity is only imposed in the x direction and the coordinates in the y-z direction are randomly sampled. in the figure on the left, we show the predicted lattice constant and the true lattice constant of this one-dimensional chains with short periodicity, where we can see that the periodicity from CGCN can actually capture the trend, although not perfectly captured. The trend is clear. And on the right, we show the predicted periodicity and the true periodicity for this long chains. And we can see that for the long chains, the trend is not clearly captured, which agree with our previous analysis that the periodicity of long structures is harder to capture than that of the short structures. And let's have a closer look at short periodicity. So before we showed that the trend of short periodicity can be captured, and we think that how well this short periodicity can be captured depends on the local expressive power of GNN. And to illustrate this point, we come up with two toy models to illustrate, which are the zigzag one-dimensional chain and the armchair one-dimensional chain, which are some, and these two chains are actually some patterns of some commonly seen one-dimensional structures in real material science research. And here we also show the dependence of periodicity on the bond length and the bond angle for these two chains. So, and to illustrate the effect of local expressive power to capture this periodicity, we can think about some toy graph neural networks. For example, if a graph neural network only connect the nearest neighbors and do not consider the bond angle explicitly, then we can imagine that this most simple graph neural network cannot capture the angle dependence of periodicity, which therefore, although this periodicity is very short, the graph neural network cannot correctly capture the periodicity of these zigzag chains or armchair chains with different angles. And if we slightly increase the power of GNN, which is to connect the nearest and the second nearest neighbors, then we can imagine that the angle dependence can be captured because the length of the triangle is known to the GNN now. But this slightly increased power graph neural network cannot distinguish the zigzag and armchair chains with the same bond length and the same bond angle. Therefore, this graph neural network cannot fully resolve the problem of capturing periodicity of zigzag chains and armchair chains. So as a people from materials discipline, this is what I can do to illustrate this problem. And actually, I think it might be important for other people, especially from mathematical or computer science people, to have some formal mathematical analysis about the power of graph neural network to capture the periodicity, even that the periodicity is short and the structure within the receptive field is constrained. Okay, so in addition to short periodicity, we can also have a closer look at long periodicity. So as we introduced before, for long periodicity, what we mean is that the periodicity is longer than the receptive field of atoms in the GNNs. And a straightforward way to improve the power to capture long periodicity is just simply increasing the number of convolutions or number of neighbors to elongate the receptive field of each atom in the graph neural network. But here we show that simply increasing these two hyperparameters is not an ideal solution. And in this figure, we show the prediction of periodicity of one-dimensional chains and real crystal structures in the materials in the materials project database by the default CGCN with 3 convolution layers and 12 nearest neighbors in each convolution, and the CGCN with 8 convolution layers and the CGCN with 18 neighbors within 12 angstrom. And we can observe some improvement for most cases by increasing the number of convolution layers and the neighbors, but this improvement is actually very limited. And we think that this limited improvement might from some phenomenon of over-smoothing and over-squashing, which prevent the use of very deep GNNs. And even if this limited improvement can be addressed by overcome this over-smoothing and over-squashing problem, we still know that the computational cost of graph neural network directly depends on the number of convolutions and the number of neighbors. Therefore, by increasing these 2 hyperparameters, we inevitably increase the computational cost, which might not be a ideal behavior for some cost-sensitive applications such as machine learning force field. Okay, all the above analysis is based on the choice of average pooling. And in graph neural network, we have another type of popular pooling function, which is sum pooling. So when we use sum pooling to predict the periodicity of crystal structures, we are actually calculating the contributions of each atom to lattice vectors. And by doing this, we may avoid the problem of long-range information, because now we only need the local information to calculate the local contribution. And we can imagine that use sum pooling may have better performance for capturing periodicity than average pooling. And in the figure below, we show that by switching to sum pooling, CGCN can well predict the periodicity of some under some cases, and will have a much improved ability to capture periodicity for almost all the cases. But here we want to say that sum pooling is not an ideal solution to the problem of capturing periodicity due to 2 reasons. The first reason is the presence of intensive property, like just like thermal conductivity or electron conductivity we mentioned before, where we cannot use sum pooling because we have to keep the supercell size invariance. And the other reason is that periodicity is actually not an extensive property, and actually we can design some toy cases to full sum pooling. For example, we can design the toy cases of double chain. And if we mix a single chain and as mentioned before or illustrated above, and mix with this double chain, we can imagine that sum pooling cannot capture the periodicity well, because in the double chain, we can see that these double chains have similar periodicity to each single chain, but the number of atoms in these structures doubles. So this can easily fool sum pooling for capturing periodicity correctly. And also, I think it might be important for people to have a more formal mathematical analysis about this issue. Okay, we just have some brief analysis about why GNN cannot capture periodicity. And here I just want to quickly illustrate its impact on property prediction. So in order to provide those missing information to GNN, for example, periodicity, here we just use a very simple way to concatenate these descriptors with the learned representation from GNN, and then feed these concatenated vectors to fully connected layers to the output. And we test this scheme with 13 materials properties and by 5 different models, which are descriptors only models, the graph neural network, original graph neural network, and the descriptors hybridized version of these graph neural networks. And we tested a bunch of properties. From left to right is thermal conductivity, total energy of the crystal structure, the phonon internal energy, phonon heat capacity, bulk modulus, shear modulus, Poisson ratio, electronic band gap, the modulus of piezoelectric tensor, electronic dielectric constant, total dielectric constant, refractive index, and the total magnetization. And we can see that for most of the properties, the descriptors hybridized version of graph neural network can beat the descriptors only model and the original graph neural network. Especially for phonon internal energy and phonon heat capacity, we can observe some huge improvement in terms of prediction error of this hybridized graph neural network. And in order to understand why this huge improvement, in this figure, we show the relative feature importance of the learned representations from GNN and the descriptors to the prediction of heat capacity by the hybridized CGCN. And through this feature importance, we can see that the descriptors are much more important than the learned features. And the most important feature is the periodicity, which is reasonable based on physics. And on the right, I just have a very brief explanation in physics. So for the phonon related property, if we only consider acoustic phonon, which is collective vibration of all atoms in the unit cell, then if we go to a textbook of solid state physics, we will know that this acoustic phonon largely depends on the lattice constant. And in addition to the phonon related properties like heat capacity, for other improved properties in this figure, we also observe that descriptors contribute significantly in the distribution of feature importance. Okay, in summary, here we propose a way to examine graph neural network for crystal structures, which is to learn and predict human designed descriptors. We found that CGCN and relied, which are 2 classic GNN models for crystal structures, cannot capture periodicity of crystals well because of the limited local expressive power, the long-range information, and the choice of average pooling as the pooling function. And we propose to hybridize GNN and the descriptors to improve the performance of property prediction. And the examination of GNN to capture human design descriptors can be actually extended to other models, other descriptors, and other systems, like other deep representation learning models, other descriptors like higher order local descriptors, and other low-range descriptors beyond the periodicity, like the point group or the space group we just mentioned, and other systems like molecules and amorphous materials. And actually, we are also interested in the behaviors of the hybridized models, like how to select the set of descriptors for the optimal prediction performance, and how these hybridized models scale with the dataset size, and whether this scaling is different or similar with the GNN only model or the descriptors only model. And here I want to answer the previous question that whether this GNN can capture the point group. The answer is no, because if you know that for crystal structure, the identification of space group, crystal system, or point group depends on the relation between lattice constants. And here we found that lattice constants cannot be predicted well. So we know that this symmetry of the crystal structures cannot be predicted well. And we have more numerical experiments in our paper revision, and we will upload the revised paper later to show this point. And here I want to thank my advisor, Professor Jeffrey Grossman, and my great co-authors for this paper, Dr. Tian Xie, Professor Rafael Gomez-Bombrelli, and Professor Yang Shaohong, and also all members in the Grossman group. And I also want to thank the Department of Material Science and Engineering at MIT, and the Research Laboratory of Electronics at MIT, and the Toyota Research Institute as my funding source. And also I want to thank my current working company, ByteDance. Yeah, that's all. Thank you.
Yeah, thank you a lot for the great presentation. I think we don't get a lot of work on crystals, GNNs, and I think it's very interesting to be able to have your kind of work and discuss like the similarities between the organic molecule GNNs that we're used to have more and this kind of structural GNNs. So first, I would like to ask for the audience if there's any question, please raise your hand or write it in the chat. I'd be happy to ask the question on your behalf.
Yeah. Actually, I have one more slide. So so
go ahead.
So the problem of the periodicity is actually mentioned in recent works about other disciplines, but as you mentioned, the periodicity in atomistic systems is less focused, and I think the purpose of the presentation is to raise the questions to the field and maybe inspire more advancement in this section. Yeah.
I think what you have proposed here right now by using descriptors and showing that using descriptors with the GNNs allow to improve the expressive power of the GNNs is something that we have seen a lot also on our side for molecular graphs, for example, where GNNs really fail at distinguishing substructures that have a lot of symmetries in them and that have periodicities in them. We talk often about the Weisweiler-Lemon issue, where, for example, it might be easier to draw there. If you have a graph that looks like two squares like that versus a graph that looks like a triangle, again, if you consider only one or two neighbors there, you will not be able to distinguish them. And this problem is very related to what you have what you have studied. And the way that like one of the most important ways that we have come to solve this problem is by using descriptors or positional and structural encoding about the different lattice to the different graph to be able to distinguish them. So in many ways, it's very, very similar to what you have proposed. And again, you can see that although for many properties, it is not required to really understand the underlying structure, there's a lot to gain by adding this descriptors.
Yeah.
I will let Brad ask his question.
Cool, thanks, Dominic. First off, thanks for saying that about WL, Dominic. That was one of the points or things that I wanted to ask about. But the second was sort of going in a different direction from the presentation. Have you looked at any of these methods with, glassy systems with dynamic heterogeneity, symmetry breaking, that sort of thing?
Yeah, that's a good question. So in this work, the answer is no. And what we look at is just the perfect crystal in some database like a materials project. Yeah, but for something like symmetry breaking in glass and some glassy systems, yeah, I think that's probably something we can continue later. And
cool. Oh, sorry.
Yeah, and actually, I think it's interesting, like in this section, and I think we can extend this examination to these glassy materials, and by using GNN to predict some descriptors that designed for glass or symmetry breaking materials to see whether GNN can capture these descriptors. Yeah.
Yeah, absolutely. And it may be, you may have an easier time looking at glassy systems in part because of the, you know, graph isomorphism test. You may find you have better success looking at glassy systems. So
yeah,
thanks for your talk. That was very helpful.
Thank you. Yeah, and I think for glassy systems, although there is no concept of periodicity, there are some other descriptors like mid-range correlation or long-range, like a mid-range interaction or correlation that we can employ GNN to examine whether GNN can capture this, like a middle range or local. How do you say? It's local periodicity, something like this.
Yeah.
Although,
So you have the alpha and beta relaxation and
Yeah.
the ergodicity breaking behavior. I think a lot of the graph convolutional neural networks may be very effective in identifying that sort of behavior.
Yeah. Thank you.
Cool. Thank you.
Yeah, I have also a question about this kind of materials. Like right now, the way you define your graph is really by the smallest periodic part. And this makes a lot of sense when you have a perfect crystal and you're studying only that crystal. But when you study the crystal in interaction with something else, for example, two thin layers of crystals, or when you study like the interaction of a crystal with a molecule, or when you study the presence of defect in crystals. I feel that this model of having a very small cell with repeated periodicity has its limitations. So how do you go into solving these more complex problems about crystals?
Yeah. That's a good question. So yeah, for these more complicated cases like the defect or like the surface of crystal, what we typically do is to first build a supercell, because supercell give us more degree of freedom. Then for example, for vacancy, as we just mentioned before, we may remove one atom from one cell. And so let me give a brief example. So imagine that we want to study vacancy in lithium, and we want to study the vacancy, the ratio of vacancy like 0.1, which is or 0.01 1% lithium vacancy. So imagine that in 100 unit cell, so in a perfect lithium crystal, maybe we have the vacancy ratio of 1%. So in this sense, we build a supercell of lithium of like with 100 lithium atoms, which is 100 times larger than a single cell. Then we remove one lithium atom to form a new cell with 99 lithium atoms, but have the space of 100. Have the volume of 100 lithium atoms in a perfect condition. So that's how we typically do this.
But wouldn't this increase your computation by 100 times?
Yes, that's the problem.
Yeah. Would it be possible to just have two small cells, like instead of having one graph, having two graphs that you learn on them simultaneously, like one that represents the lattice with periodicity, and the other that represents a slightly bigger lattice. I don't know. Perhaps it's not clear. Like it needs to be thought a bit more. But what about if you want to study like the interaction of two crystals together? Like now you have to consider the entirety of like the the entirety of the slice of the crystal. No.
Yeah. So when we study the surface or interface, we first also build a supercell and then cut the supercell to form the surface. And for interface, we just put two surface together to form the interface. Yeah, that's something like I would say the surface and the interface problem is a complicated topic in material science. Yeah, and I think machine learning toward those surface problem and the interface problem is we are lacking this study of machine learning to these more complicated systems. Yeah, that's I think a hot topic next in the next few years. I would say.
Okay, makes sense. And what if you want to study like properties that are non-symmetric? Right now, the GNNs that are being used are highly symmetric, but we can easily imagine, for example, ferromagnetism, which is non-symmetric and depends on a certain direction. One thing that I was wondering with the one of the descriptors that could be added, for example, in the crystal structure, like typically, if you have an atom connected to like other atoms like that, there's no way to tell which one is up, which one is down, which one is left, which one is right, because this like basically you have rotation invariance there. But by forcing the convolution to always being symmetrical, you make the system weaker and unable to detect certain edge cases. So I was wondering if techniques similar to what is used in computer vision could be borrowed, where you would have a directionality. You can define, for example, this one to be the atom on the right and on the upright, and this one being the bottom right, and up left and bottom left, and have some kind of descriptors like that, but then augment during your training, augment with the different rotations of that same crystal to get similar properties. In many ways, this would make the model more expressive because the kernel is no longer forced to be always symmetrical.
Yeah, I think a recent advancement of equivariant neural networks is just do this thing, correct? Right? Because using equivariant neural network, you essentially have rotation equivariance. So, like for some property that depend on the direction. Like for example, if we want to predict a vector from the bottom left to the upper right in your crystal graph, then when we use a equivariant neural network, and if we rotate the input, then the vector will also rotate accordingly. So I think that's probably the technique to consider this rotation, to consider this rotationally invariant or equivariant problem. Yeah, and also equivariant neural network can be used to predict those vector or tensorial property by just outputting this correct tensor, right?
But right now you seem to be using only like mean and sum aggregation in.
Yeah. In this work, yes.
Yes,
in this work, yes. Yeah, but yeah, this work is done like in 2021, and we initiated this work. But later, I think in 2022, the concept of equivariant neural network really boost. So yeah, we missed the boost, but we mentioned in our paper that equivariant neural network should be examined later. Yeah.
Yeah, no, that makes a lot of sense. I think without equivariant neural network, you will be missing many of the directional properties. And especially, I think like when you study crystals, one thing that is very important is the propagation of phonons, and the propagation of phonons is often very directional as well.
Yeah.
All right, everyone, me again, and doing this outro as always. And as always, I have to tell you, we are very happy with you watching these videos, but we would much rather have you in our live sessions and asking the questions and participating in our discussions. So for that, all the details are down in the description, and see you there or see you next week in the next video.